This is the screencast for section 7.4, example 2, applying the definition, basically the definition of length of a curve. So we're going to find the exact length of this messy curve. Basically you have 4 square root 2 over 3 times x to the 3 halves minus 1. Now x to the 3 halves is a power function whose exponent is greater than 1, so I can already tell you that the right side of the equation is going to look, well, let's see, shift down 1. It's going to look like that. And we're stretching from 0 to 1, so I know the length is going to be greater than 1. So that'll help me determine if my answer is correct. But let's start to set up the integral. So I'm going to be taking the antiderivative from 0 to 1. So I'm adding up all these little teeny tiny straight segments to get the length of the curved segment. And those segments are going to stretch from 0 to 1. Then the formula says I need the square root of 1 plus the derivative squared dx. Now the derivative of that is going to be drop the 3 halves down, then times 4 square root 2 over 3x to the now 1 half, and then of course the squared was already there. The minus 1, the derivative is 0. So let's simplify that a little bit. Much nicer. And let's square it. Even nicer yet. Now I have something that I can work with. So now I can take the antiderivative by hand, simplify, use fundamental theorem of calculus part 2, and I get 13/6. So again, the distance is a little bit, or the length of the curve is a little bit longer than 1. If we're stretching from, or we're trying to find the length of the curve between 0 and 1, a straight distance would be 1, but this is a curved distance, so a little bit longer than 1 unit. The now try problem number 11 says find the exact length of the curve analytically by antidifferentiation. You will need to simplify the integrand algebraically before finding an antiderivative. Now generally that's always a good rule of thumb because you'll make that antiderivative much easier. So for number 11, I got another complicated-ish problem, 1/3 x squared plus 2 to the 3 halves, and I'm going to find the length of that curve between 0 and 3. Well, I know I'm going to take the derivative eventually, and instead of doing it within the problem, I'm just going to take the derivative ahead of time, so I eliminate some possibility for mistakes if I do it separately. So the derivative, I take the 3 halves, put that down as a coefficient. Now the exponent is 1 half, but of course chain rule says I'm going to have to multiply by the derivative of x squared plus 2, which is 2x. Now I can simplify those coefficients a little bit more, and then now I have an easier derivative to work with inside my formula. So my formula for the length of this curve is going to be the antiderivative from 0 to 3 of the square root of 1 plus the derivative I found squared and then dx. Well, I see this 1 half squared, which is nice. Now the x is also being squared, so when I simplify that exponent of 2, I'll get x squared and then the x squared plus 2 without an exponent, or exponent of 1. Now I can distribute the x squared. That looks familiar to me. That is a binomial squared. That's x squared plus 1 squared. And then I'm taking the square root of it. So that simplifies even further to just x squared plus 1. That is a very easy antiderivative to do. So all that algebra, all that simplification and rewriting things makes this antiderivative much easier to work with. So now I take the antiderivative, use the fundamental theorem part 2, and I get 12 units of length. Now that seems a little excessive. A straight distance between 0 and 3 would be 3 units. 12 units seems very, very long. But remember, we're dealing with an x squared curve here to the 3 halves, so it's even a higher exponent. So there could be a really long distance between 0 and 3. And graphing on your calculator would probably give you a more accurate representation, but that's my non-accurate representation.